Hi guys, so continuing on with the lecture, sorry to run off, but this is going to be part 2 of 2 for Thursday, May 7th lecture. And we're going to be working the problem, like I said, that comes from this PDF that's online in the handout section in files in your Canvas folder, and it's under rotations, beamtorque.pdf. And what it looks like is you're going to have a beam, and that beam is sitting vertical on what is a rough surface. And the beam has it has a height of h. So not L, but h. It has a mass m. And there's a force that is pulling on it to the right. And that force, for now, is going to be pulling to the right at a height of n times h. And so n is allowed to be between 0 and 1. Of course, 0 meaning you're pulling on it right here at the bottom, and 1 meaning you're pulling it right at the top, at h. And in addition to the force, there's also a rope right here at an angle of theta with respect to the vertical that's attached to the floor at this point. So because this is a rough surface, that means there's friction here, and of course it's going to be a static friction force because, excuse me, there's no relative motion at this interface between the plane and the beam. So this is the setup, and the idea, this is an equilibrium problem, meaning again that the sum of forces are going to be 0 and the sum of torques are going to be 0. And the idea is that you're going to pull on this beam, and you're going to pull on this beam more and more, and ultimately you're going to be looking for the point, at which this thing starts to rotate or move. So part of what you're working towards is finding what is the maximum value of pulling that you can have before rotation and translation occurs. So also, as an in-between step, I'm going to have you solve for the force of static friction. And knowns in this problem are going to be N, F, M, theta, and the coefficient of static friction. Okay, so we have our conditions here: no translation, no rotation. And to begin, I'm going to do what you should always pretty much do for these kind of problems, which is to start by performing a force body diagram. Now, we already have our force here, F, acting, as we said, some height of NH above the bottom. But we have other forces too. We have the force of tension acting here up at the top. This is a uniform beam. And so the center of mass is in the geometric center. And that means that gravity, mg, is acting there. There's contact with the floor. And so there's also a normal force acting upward. And then there's a force of static friction. Now, I'm going to go ahead and draw the force of static friction in. It acts here, and it's acting to the left. And I'm going to justify to you why that is the case, why it's not pointing this way instead. because it's possible. I mean, there's a force of tension here, but the way that I justify it is, for sum of torques equals to 0, I can choose my axis of rotation anywhere when it's not moving. And if I choose the axis of rotation to be here, there's 4 possible contributing forces, right? There's a force of, so let me just kind of lightly write this in. There's the force of tension will not contribute because it's acting at the axis. F will contribute, causing a rotation this way with respect to the axis. The normal force will not contribute because there is no perpendicular component of the force. And same with gravity. There's no perpendicular component of the force to the r vector. So that leaves only the force of static friction, which causes a rotation this way, to counteract the torque, which causes a rotation this way from F. Because with this choice, these 3 forces do not contribute. And so the force of static friction has to act this way for the sum of torques to be 0. Okay, so I am not going to be choosing my axis of rotation there. I'm actually going to be choosing my axis of rotation at the bottom so that I can follow along with what I did. So let me kind of get rid of that. Okay. And let me put my axis where I'm going to for this problem. And I guess I'll make it a little bit big. Here, there's my axis of rotation. I can choose it anywhere, like I said, but honestly, there are 2 forces acting here, static friction and normal force. So when I talk about the sum of torques equaling 0, and I say that I have a torque from every single force, or at least it's possible I have a torque from every single force, I actually have 5 of them here. If I place this in a proper location, I can right away say that the torque from normal and the friction force do not contribute at all because their R values are 0 based on my choice of the axes. That leaves 3 possible contributors: gravity, force F, and tension for torques. And I'm right away going to argue that gravity does not contribute, and that's because if this is the r vector right here, mg is entirely parallel to the r vector. So if the magnitude of a torque is r times F perpendicular, I can say that for gravity, F perpendicular equals to 0. All of the force is parallel to the r vector. And so really that just leaves F and tension. I don't have the same problem with those 2 because all of the force F is perpendicular to the r vector for F. And if this is the r vector for tension, I can at least break part of tension up into a perpendicular component like this. So looking at tension, let me go ahead and work on that. Here's theta. This will be T sine theta and T cos theta. And it's going to serve me well to kind of rewrite this force body diagram with the parallel and perpendicular components. So let me just replace T with T sine theta, T cos theta. And then I'll have this force of F here. Let's redraw this whole thing. And you guys see that I've been very careful to put the forces exactly where they're acting on the beam. Okay. So with this axis of rotation, again, F is already ready for me, and now I can see the perpendicular component of the tension force is just T sine theta. So I'm ready to write out what is the force, or the torque from the force F, and what is the torque from tension. And for force F, I need the value of its r vector. And that's just going to be this height, n times h. And all of F is perpendicular. And with the choice of axis of rotation that I've chosen, this is going to create a clockwise rotation. So that's in the minus z hat. For tension, the magnitude of its r vector with respect to that axis is the full length of the rod h. And t sine theta we've already discussed. T sine theta is the perpendicular component of the force. And this rotation is counterclockwise. It needs to be in order for these to sum up to be 0. And so in total, I'll have NHF minus plus HT sine theta z hat equals to 0 z hat, or minus NHF plus HT sine theta equals to 0. And I get one equation from the torque equations. That leaves sum of forces in the x and the y. Well, in the x, I have one positive F and two negative forces, F sub s and T sine theta. Yeah, Z. So from sum of forces in the x equaling 0, I'm going to have F minus T sine theta minus F sub s equals to 0. Second equation. From sum of forces in the y, I'm really prepped here to keep going. I just have three, t cos theta, mg, and normal. Normal is positive, and mg and t cos theta are both negative. Third equation. So I'm going to solve for the force of static friction, and here it is first in my problem. I'm going to solve for it in terms of known quantities. So again, let me just kind of highlight this box of knowns over here. And so right away, you can see that solving for the force of static friction will be F minus T sine theta. Well, T is an unknown here. But lucky for me, well, heck, I have another T sine theta right in here. And I can solve for T sine theta. The heck, I'll do that from this equation. So from, we'll say equation 1 will give me T sine theta equal to n times F. So the h's just go ahead and cancel right on out here. And so I've now solved for the force of static friction. It's equal to F minus n times F, or F1 minus n. So that's kind of the first step that's asked for. And what this is telling me is that if n equals to 1, and I'm pulling all the way here at the top, it's really telling me there's no kind of real need for the force of, that the force of static friction is effectively zeroing out. And then at the top, that T sine theta is enough to kind of counteract that, because look, T sine theta is n times F. So at the very top, when n is equal to 1, it's just telling you that the force of friction is enough to overcome T sine theta. They'd actually have exactly equal and opposite torques, giving you torque equal to 0 there. So there won't be a need for the force of static friction. When this is pulling up at the top, this goes away to be 0. From here, I know that the more that I'm pulling on this F, right, so I'm maximizing the force with which I can pull here, that as a result, this is going to be compensating here and growing larger. So I want to now look for kind of F max, and I see that in the equation, that the more this is, the bigger this is going to be. So now I'm going to kind of maximize F sub m. So I'm going to need that equation F sub s equals to F1 minus n. And so to maximize this, I'm maximizing, so to maximize the force of static friction, I'm maximizing F. And that's what I'm looking for. What is F max? That's the next thing I'm solving for. Well, the force of static friction is mu static times the normal force. And let's take a look at my equation for the normal force. Here it is. So I'm going to use that, and I'm going to use this equation right below it. To help me solve. So the normal force, you can see from that highlighted equation, is mg plus t cos theta. Well, I also know that t is equal to nf over sine theta. And so I can solve for n equals to mg plus nf cosine theta over sine theta, or n is equal to mg plus nf cotangent of theta. And then I'll take this normal force and I'll plug it into here, my maximized force of static friction, and I'll get mu static mg plus mu static nf cotangent theta equals to F max 1 minus n. Now, this is not just any F, this is also F max. So I should be careful here. I'll be plugging that in. And so you can see that in order to solve for F max, I need to bring this over here, and I'll have mu static mg equals F max 1 minus n minus F max mu static n cotangent theta, and then factoring this F max out of both terms here on the right. I can now just solve for F max. And I'm done. I think this is interesting because this is also telling me that associated with each F max is a very specific angle theta. And so for one F max, there's a given theta. So for different angles, and don't forget the angles are associated with the direction of the rope here, right? For different angles, there are different values of F max that I can have. So for instance, as F max, or as theta, well, as theta goes to 0, the cotangent of theta becomes infinite. And in fact, F max will then kind of go negative. So in the limit that the rope is kind of pulling straight down on that rod, there's really no need for, there is no kind of F max associated with that. It just becomes minus 0. Minus 0 in that limit. As theta goes to pi over 2, cotangent theta goes to 0, and F max is kind of at its maximum value that it can be as mu static mg 1 minus n. So this is like F max max. In the notes that I have, I play around with this idea of the fact that F max can't be negative. So minus 0 doesn't really make sense here. You see what I mean? F max is the magnitude of a force. So I concentrate on the fact that this denominator can't be 0, right? It's got to be greater than 0. You don't want it to be negative. And from that, you can get a condition that tells you that 1 is greater than n plus mu sub Sn cotangent theta. Factoring out an n over here, you can kind of take a look at what n is doing. And n has to be less than 1 plus mu sub S cotangent theta. And so, again, there's, for each value of theta, there's now an n associated with it based on this condition. So this is a little bit better than what we were doing, playing around and getting these kind of -0 numbers here. And we see there's a limit on what n can be. And what that has to do with, of course, is how high up from the ground, right? N is just this height. How high up from the ground you have to be for a given theta. And remember, theta is associated with the tension force. So if theta equals to 0, this is negative. So for the theta equals to 0 case, cotangent of theta is infinite, and 1 over something infinite goes to 0. So n has to be less than 0, effectively equal to 0. So as theta goes to 0, and you're pulling down like this, the force is now acting here. So it can be large, but it's not contributing to the torque anymore, right? And neither is this tension force. It completely doesn't, it's become completely parallel at this point with respect to this axis of rotation, and therefore it doesn't need this torque anymore. So it moves the force over here to where it contributes 0 as well. If theta equals to pi over 2, cotangent equals to 0, and we have that n can be less than 1. It can be actually anywhere. So as you pull out with the tension force completely perpendicularly, F max can be anywhere that it wants to be along here, but it's pretty much saying that n is going to act up at the top, that it can act up at the top to kind of correspond to this pi over 2 angle. For angles less than that, F max is going to be restricted to values kind of, below the value of n as dictated by each angle until it goes to 0 again. So for a given theta, there's a given range of n's that's allowed. That's interesting. Anyhow, that's that problem. And again, you have the handout for that. And this concludes part 2 of 2. Next time we meet, we're going to start on chapter 11, and maybe we'll work a few more problems like this in the recitation. All right, talk to you later. Bye.